Hello, everyone. My name is Harry Koehnemann with a company called Scaled Agile, and I'm excited to tell you that I am presenting at the LPPDE conference next week. May 14th, I believe, is the date. So this is a little preview of the talk that I plan to do. I'll be giving a talk and also be participating in a panel session. So I hope you're all registered and find this useful. And if you're not, please get registered and come join our conversation. I want to take you back to the 1960s, and this is a United States story, but some people, if you're old like me, you'll probably remember it. Actually, I was alive when they landed on the moon for the first time. But back in the 1960s, there was a race for space, right? To get to space first, and President Kennedy of the United States challenged our country, the United States, to go to the moon, right? If we want to win the great space race, we're going to go to the moon. And that was followed up by 7 short years, right? In 1962, we put a man in space, but had no idea about the kinds of systems we'd need to go take someone all the way from the Earth to the moon, land that person on the moon, and then bring them home safely. Yet, we made that commitment, and 7 short years later, less than 7 years later, we put the first man on the moon, Neil Armstrong. So how did that happen? Well, I want to say one more thing about that, where Neil Armstrong gave his famous quote, "One small step for man and one giant leap for mankind." And that's a pretty famous quote that you may have heard, but it really wasn't one giant leap, right? There was not just that first launch. We didn't get it right the first time. There was a series of smaller leaps, less giant leaps. There was the Mercury program and the Gemini program and the Apollo program. And within each one of those programs, there was a series of other smaller launches, right, where we learned things, right? How we put men in space, how long can people stay in space? How can they work in space? We did spacecraft design, and did reentry procedures, going to space and coming back into space. Ooh, wrong direction. And I apologize. The Gemini program. We worked on spacewalks and rendezvous and docking procedures and mock-up lunar modules. We had a mock-up lunar module still orbiting the Earth, but we worked on the rendezvous and docking procedures. And then we also worked on the automated reentry procedures that we needed for the Apollo mission. And not to belabor the point, but there were even more missions in Apollo, right? Putting things in space where we learned, again, more aircraft design, up to Apollo 10, which was a whole dress rehearsal. We went all the way to the moon, back, circled it, did everything but land on the moon. We took all the equipment, all the procedures, and that was Apollo's 10 mission, right, to put the man on the moon. Whereas we mentioned before, Neil Armstrong gave his famous quote of "one giant leap for mankind." But we see that, back in 1962, we were not smart enough to design the Apollo 11 spacecraft, the lunar landing module, the docking procedures, right? No amount of additional specification and requirements detail, or no more detail to a schedule, is going to reduce that uncertainty, reduce that risk. Right? We cannot plan or specify our way out of that type of uncertainty. The only way to do that is to learn. And in fact, that was true. Back in the 1960s, through the Mercury, Apollo, and Gemini programs, we went to space almost every quarter, right? Every 3 to 4 or 5 months, we were going into space and the operational environment to learn, right? And so if we looked at an agile perspective of this, well, we'd have a roadmap of learning milestones that we need to accomplish, right? To put someone on a lunar landing and return, well, we had a series of learning events we had to happen. There's a backlog of the work needed to create that. What are the different launches going to demonstrate for us? Every time we go to the operation, right, we're learning. And of course, we're going to evolve the solution, right? We don't know what that Apollo 11 rocket is going to look like, but we know that incrementally we're going to learn to be able to make that Apollo 11 rocket. So I wanted to bring this up because, this notion of incremental learning isn't new, right? We've been doing it for quite some time. And we just kind of seem to have lost our way. We seem to have regained our way, though, through digital disruption. I want to take a little sidestep and talk about that for a minute. So if you're a safe person, or say you've probably seen this in some of our slides or material, but here we talk about where digital disruption came from. So a researcher was back in the .com era in the late 90s. There was a researcher, Carlota Perez, who was wondering, have we ever seen this kind of technological disruption happen before, like software was doing in the 90s, right? A mass amount of capital is flowing into these startup companies, right? And then, and then what happens after that? Well, she looked back at other technological revolutions, oil and mass production, steel and heavy engineering, and she found the same patterns occurred where a mass amount of capital flows in, like in the roaring 20s in the United States anyway. In Detroit alone, Detroit, Michigan, there were 300 automotive companies. there's a turning point where the victors emerge. And for us anyway, Ford and Chrysler and General Motors, they emerged as the victors. The other 270 got consolidation or went out of business, right? The victors emerge in that deployment period. And then there's the you are here, and the laggards try to keep up. And that's been true in every one of those industries. But another important point that you may not be aware of is that Carlota Perez also noticed that each one of those tech revolutions identified a new way for managing work and people. And the traditional, project management approach that we use today or have historically used today, well, that was developed back in Taylorism, right? That was back in the age of steel and heavy engineering. What is the new way of managing work and people for this age of digital and age of software? And we're going to posit that is a lean agile approach, one that's focused more on continuous learning. And we saw again you are here, the victors have emerged already in many industries, right? I did a bunch of work for Motorola back in the day, right? They dominated the cell phone industry until Apple and Google came out with the smartphones. Advertising, digital retail, Amazon has disrupted retail. Again, there's many industries that have been impacted and completely disrupted by digital. We're now seeing that same disruption happen in the cyber physical industries, right? All those other industries were software, but now we're seeing space being disrupted, automotive being disrupted, aerospace being disrupted. People that build the cyber physical systems, right? They're going through their digital disruption period, right? The victors have not emerged in these industries yet. They have in other software industries like retail, or nobody goes to Blockbuster anymore. So there's a series of practices that we think are critical for accelerating delivery and doing this type of learning, right? And so here's a series of practices that we think are critical. I'm going to run through a few of them here, and we'll talk about some of them and some of the other ones next week as well at the conference. So let's jump into shift left. Let's talk about it first. So the goal here is to shift everything left. Why is that so important? Well, if we contrast a traditional or more waterfall type approach, I've done some work at NASA, and NASA, not NASA back in the 60s. This is NASA, our aerospace, our research organization, the National Aeronautics Space Association is NASA, and they do all of the research for space launches. NASA of the 60s was more like the incremental delivery view at the bottom, right? We're going to go incrementally build the solution. We're going to learn and make adjustments along the way. As I mentioned before, somehow we lost our way, and we do very large batches of requirements, design, implementation. In fact, our goal is really just to get one launch correct. So we have these long development cycles that delay delivery and feedback. We're not focused on what's the minimum thing we can do, put in an operational environment to learn, right? And that really limits our ability, right? These things that we're building, they have technical uncertainty, market uncertainty, user uncertainty. Is this really the product the user needs or wants, right? And so we may wait years to getting it in the hands of users or validating technical uncertainties and other business assumptions before we get that kind of feedback, right? So we want to move to more of a model that's more of a plan, do, check, adjust, right? We want those incremental, what we call the PDCA cycles. Plan something, do it, check, and adjust. And as Dontar Osterwald tells us in his very famous book, Lean Machine, that especially as we scale this, right? Teams can do small incremental learning cycles, but really the integration points are what control product development, right? We don't just want teams learning. We're not trying to optimize teams. We're trying to optimize entire value streams. We want value streams to be learning. They're doing their PDCA cycles. And then especially as we scale to some of these aerospace, automotive systems, defense systems, where there are literally thousands of individuals or tens of thousands of individuals spread across multiple organizations and companies, where we really have to scale that integration. And sure enough, we see that right in the automobile industry today. In fact, back when I was working 10 years ago in the automobile industry, they were on a regular 6 or 7 week cadence, right? Every 6 weeks, we were working on an infotainment supplier, and every 6 weeks, we were delivering new firmware up to our parent company, up to the OEM. It certainly new firmware every 6 weeks, and sometimes new hardware or adjustments to the hardware, moving dip switches, or making sometimes it was brand new boards, sometimes it was just adjustments to the board, soldering a wire, etc. So certainly we want the whole system to be learning, right? And those integration points are critical. So how do we do this? Well, software's kind of led the way, and they've developed a thing they call the continuous delivery pipeline. And what that is a series of automation for the workflows and activities that we need to take a small increment of value, something that we need to develop, test it, and release it into an operational environment, and automate that. And so if you look at some of those companies that were the unicorns back in the day, those digital disruptors, Amazon, Google, Netflix, they were not just only investing in the solution, they were investing in the infrastructure that builds the solution that builds the solution. So they invested heavily in the ability to hypothesize something, build it, measure it, and learn from it to be able to make adjustments. And that's really the goal of those companies. But it doesn't happen without investment. If we only focus on investing in just a solution, we're not investing our ability to learn faster than the competition, right? Which is critical. So the software contingency pipeline is pretty well known. You might have heard things like Kubernetes and infrastructure like that. And there's already, in fact, open source, freely available products that the software people can leverage. But that technology really doesn't apply necessarily to hardware, right? The software pipeline is well known. They have a 20-year head start. But I would argue that the hardware community has just recently begun its journey, right? So we're in more of the unicorn stage for the hardware development, and the victors will emerge, certainly, just as we saw the victors in software. Learning certainly occurs in 3 environments for hardware. So a lot of times we think of hardware, we think of, I've got to build an entire car, or to build an entire aircraft, or build an entire rocket. So we have to build something to put it in the operational environment. But we can also learn digitally. Right, so there's virtual environments with modeling and simulation, and there's been a big push for digital shadows and digital twins. There's also prototype environments where we can do physical mock-ups. There's services out there that will do, for example, PCB, printed circuit board in a day service. So I don't have to have the 3D printing technology and infrastructure. That's a third party now, right? My company doesn't need it. Instead, I will send them my CAD drawings, and they will ship me the next day or next couple of days a series of boards. So I don't have to wait months or weeks or potentially months to get that turnaround. I can get the turnaround more quickly. And certainly I've worked at companies and organizations where a lot of times it's not even just the technology, it's the permission to actually turn the boards over. I was working with a defense company on doing missiles, and they had the challenge. It would take 7 to 8 months to turn a board, right, to spin a board. And it wasn't just because of technology. Certainly there was some, supplier issues and whatnot, and contract issues, but a lot of it was just their requirements. They assumed that every board was going to be in a missile that was going to be, that had to be given into a production environment, that was going to be an operational environment and had to work for 30 years. Instead of understanding that some of the boards we're manufacturing are engineering versions, right? They're engineering samples, and we want to iterate faster. They didn't have that notion of that understanding. So we were able to shift that cycle from the prototype environment loop there from 7 to 8 months down. I think we got it down to 6 weeks, 5 or 6 weeks by the time we found a new supplier, et cetera. And you could shift it even further than that, right? This was 9 years ago kind of challenges. And then certainly, we eventually do move into the operational environment, right? Make changes there. And we see organizations like Tesla, most manufacturing environments, that operational environment, they're optimized for repeatability. We want every part to be identical to the previous part. That's our goal, right? No variability in manufacturing. We're rethinking that. Organizations like Tesla, they will make a change to I think the stat is 5 or 10 changes in every manufacturing line every week. If we have a better heat pump, why are we going to wait for the next model year or maybe even the next vehicle redesign to get that better heat pump into the customer's hands or our business hands? It may consume less power. It's cheaper to manufacture. It's whatever that new heat pump is, or that new part is. Let's put that in the next car, not the next vehicle redesign or next model year. And what we're seeing is exactly what happened in software, where the software development group got much closer to the operations group, so that if I have a change, I can get it in operations much more quickly. We're seeing engineering and manufacturing, or engineering and production, getting much closer together as well, so that engineering is really working side by side with manufacturing. So we still have our virtual and prototype environments, but we even get into that manufacturing environment as well as quickly as we can. Really what that takes is it takes some investment. We don't just invest in building the car or the missile or the hearing aid or whatever the manufacturing product we are. We have to invest in being able to continuously deliver that product. And we see examples of this, right? So modeling and simulation. Saab's a very famous one in the Agile community because they modeled the entire grip and fighter, and they're able to simulate small changes and get fast feedback on those changes in their modeling and simulation environment. I love the fact that all these example companies aren't all didn't just exist 20 years ago, right? General Motors, 100-year-old company, they cut the Hummer EV delivery time in half through their investments in digital engineering. This is a kind of an old story, but 4 or 5 years ago, when the CEO of GM went to the Hummer team and said, "I need an electric truck in 3 years," and they said, pushed back and said, "Well, our normal turnaround time is, for new vehicles, 5 to 6+ years." And she said, "Well, you have 3, because this is 4 years ago. The pressure for electronic cars, especially electronic trucks, is huge. We make a lot of money off our trucks, right? We're one of the biggest truck sellers, and so we need to have a digital offering ASAP, as soon as possible." And certainly, and so the story goes is that they went to there was already a digital engineering research team, and they brought those folks in. We said, "We're going to be your first design customer. We're going to be your first customer to make a real vehicle with it." And they did. And they cut the time in half, right? Instead of 6 years, it took them 3 years to go from inception of the concept car, or inception of the program, all the way into manufacturing production, and delivery to dealers. And they cite that through that investment in digital engineering. And there's other rapid prototyping examples, right? And we already mentioned Tesla, right? They're optimizing for change. They can get a new innovation in every car, not just every new model year. SpaceX, they invested in the world's largest 3D printer. It's on site down in Texas where they launched. So instead of having to manufacture parts someplace else and ship it by rail over to the launch pad, they just manufacture the part right there on the launch pad. Engineering, manufacturing, launch, productions, all done in the same place. They have another great example where we don't weld and then later on hand it to somebody else to validate the weld and verify that it's safe. They attached an X-ray machine to the welder. So as they're X-raying, they're validating the weld in real time, right? So just things like that. Just how can we shift things left? That whole shift left mindset. All right, so I think I wanted to talk for you about 20 minutes. That's one example. I gave you a list of different practices that we think are critical to understanding, how to apply lean agile practices in the age of hardware and cyber physical systems. So I hope you're able to join us next Wednesday, on the 14th. And my name is Harry Koehnemann. Hopefully I'll see you next week. Have a good day. Thank you.